In this video, we look at more examples at limits to infinity. In this particular example, the rules from the previous examples don't actually change. We take a look at the bottom of the function, and we look at the largest power of x in the denominator. That's this 4x to the power of 5. So when looking at this limit, we're going to go ahead and multiply the top and the bottom by 1 over the largest power of x in the denominator, just like we had done in all other examples. So for this one here, when distributed in, you'll notice that we're going to have this piece here is the piece that ends up being constant. When I distribute this top piece in, it happens to be the first term that is constant. So simplifying this provides me with the limit as x goes to infinity of 3 minus 4 over x to the fourth plus 5 over x to the fifth divided by 2 over x to the fourth minus 7 over x squared plus 4. And all of these individual terms that are divided by x to the power of something with a constant in the numerator, those all go to 0, and leaving me with 3 divided by 4. Again, this is not a unique example. It behaves very similarly to all other examples in terms of the limits to infinity. The only difference, however, is we've got to make sure that we're very careful to ensure that we're looking for the function if it's not in general term or general form. So this function up top is actually in general form, where it's in the largest power of x's first in decreasing order. We can't just assume that that first function right there, that first term, is in the largest power of x and decreasing order. If it's not, we should either mathematically rearrange it, or at least in our minds rearrange it. The next example we're going to look at is an example such that it's not in general form, and it's not even in simplified form. We can't have it written out in the form that we wanted it. Now what we could do in this particular example is we could go ahead and multiply everything out, giving me the limit as x goes to infinity on top of x times 1, which is x, and then plus 2x squared, and then plus 3, and then plus 6x. We could do this same exact thing with the denominator, but what I'm going to recognize is I need the largest powers of x on top and on bottom. The largest powers of x would be me taking x times 2x. It's all the x terms multiplied together here. That's this term right here. And then if I do the same thing with the denominator, that's going to give me just x squared. There are a lot of other terms that are going to be here, but knowing that the largest power of x in the denominator is x squared and the largest power of x in the numerator is x squared, if we look to the previous examples such that any time that the largest power of x was somewhere in the denominator, we multiplied by that largest power of x, and that was the only term that didn't end up being 0 when we evaluated the limit. So we could bypass some of this heavy algebra stuff by recognizing that I'm going to multiply the top and the bottom of this function by 1 over x squared, and that every term that doesn't have an x squared in it should end up going to 0. So again, I'm going to make the assumption that that's what's going to happen. All the extra terms plus dot dot dot, those are all going to be 0 when I evaluate the limit. This is the only term on top that's not going to go to 0. It's going to go to a constant, and all the other terms around it are going to go to 0. So this will be the limit as x goes to infinity of simply 2 divided by 1. And again, it's 2 because it's 1 over x squared times 2x squared. That's going to give you the 2. And then over here it's going to be 1x squared over x squared, giving me 2 over 1. This limit is then going to be 2. This should be a reminder to some extent of how the horizontal asymptotes worked in pre-calculus. This actually has a very direct relationship to the rules for how you evaluate the horizontal asymptotes. It might not seem that algebraically, but remember, we looked to the largest power of x in the numerator and the denominator, and we talked about the powers on top and on bottom. If the powers were the same, the coefficients divided by each other gave us a horizontal asymptote. If the coefficients weren't the same and the top power was larger, we ended up saying that there was no horizontal asymptote. And if the bottom power was larger, then we would say that the horizontal asymptote is y equals 0. Again, in the previous examples, we came to a conclusion of y equals 0, or 0 for the limit, an infinite limit, and then a coefficient of 3 divided by 4, or the values divided by each other, depending upon the largest powers of x's.